All right, so in this podcast, we're going to be talking about the last topic in our Unit 12 packet, which is calorimetry. And this is going to be based off of the calculations we learned how to do on page 11. So please make sure that you either took those notes in class with us already or go watch the notes video that I posted covering that, because this is all related to that stuff. So first of all, what is calorimetry? It's the idea that when two systems change together or near each other, when they're exchanging energy with each other, we can use data from one system and the temperature changes that we can observe, the energy changes in one, to figure out information about the other. So this comes back to the idea that as heat is exchanged between two systems, there's no heat lost. That law of conservation of energy, the first law of thermodynamics that we already talked about, means that all of the heat that's being lost from one of those objects is the same heat that's being gained by the other object. So there's no heat lost. This amount of heat is going to be the same. Now, if I asked you a simple question like, what would happen if I put a hot metal cube or, object into some cold water? What would happen to the temperatures of that metal and the water? Would they both get warmer, both get colder? Would the water get warmer while the metal gets colder, or would the metal get warmer while the water gets colder? And because the metal is starting off hot and the water is starting off cold, hopefully that you can come up with, even before I teach you more details about this, that the water would get warmer because it's going to be absorbing some of the energy from that hot metal, and the metal would get colder. If we had a kind of visual temperature scale of those two objects and their initial and final temperatures, they would start off at different temperatures, but they would both change temperatures and exchange energy until they're the same temperature. As long as you have one thing that's warmer than the other, it's going to keep giving energy to that other object until they come to the same final temperature. That's going to be an important thing to remember for these next couple of problems. And even if the temperatures don't change by the same amount, I purposely made the water heat up by a smaller amount than the hot metal cooled down. The total amount of energy is going to be the same. Remember, energy is different than temperature. So heat energy lost is going to be the same as the heat or energy gained, but the change in temperature of one object here, the metal, is not necessarily going to be the same as the temperature change of the water. If the water gets warmer by 10 degrees, it does not mean that the metal gets colder by 10 degrees. Now, we are going to have to kind of calculate some of those numbers, and so it is going to come back to that idea that heat lost equals heat gained. And like I said, we're going to start plugging in a little bit of stuff from our calculations in class. Remember, we used heat, the variable in our equations was Q. So we could kind of change heat lost equals heat gained into Q lost equals Q gained. And here, because we're talking about metal and water, we could be specific about Q metal equals Q water. And because both of these things are going to be changing temperature, we could use that temperature change equation, the last equation that we used at the bottom of the last page, and substitute in that MC delta T for both our metal and our water. And it is going to be important that it's the mass of the metal that we plug in on the metal side, not the mass of the water. They are different. Their specific heats, those C values, will be different. And like we just established on the last page, their temperature changes will be different. So these are the types of problems we're going to be solving here. We're going to be using this equation, which is really just two MC delta T problems set equal to each other because their energies are equal. And we're going to be solving for one of these unknowns. Those first couple of problems, we're going to be solving for the specific heat of the metal so that we can use that to identify the metal. But we can solve for any of these other variables. If we wanted to know the mass of a metal, if we know its specific heat and how much its temperature changed when we put it into water and measure the temperature change of the water, we could figure out the mass of the metal without having a scale. We can use this to find lots of unknown quantities. What these problems are really going to come back down to is some very careful finding variables. So we're going to be using that equation, MC delta T equals MC delta T for metal and water, in these next two problems, which means the first thing I'm going to be doing, you're going to see me list out metal MC delta T, water MC delta T for both problems, just to find all the numbers, figure out what we got and what we're looking for so we can keep everything straight. Staying organized is going to be the biggest battle with these types of problems. Now, keep in mind you have a table there which has all of these C values, the heat capacity values for all of the substances we're going to be dealing with, and all of them are going to involve water. I know we've seen water be 4.184 before, but in this table, since it's 4.18 here, that's the value I'm going to use on this page with these problems. And each of those first two questions asks us to identify what metal was put in the water. Because every metal, every substance has its own specific heat, we're going to be calculating those C values, their specific heat values, and then we're going to come back and look at this table to figure out what element we got, what metal we have in this water. So, let's jump into that first problem. This says that we have a 55 gram sample of metal, so that means the mass of metal was 55 grams, and it's starting at 90 degrees Celsius, and it's dropped into a container with 250 grams of water that was originally at 22 degrees Celsius. It tells us that the final temperature of the system, so both the metal and the water's final temperature, is 23.4, and then it asks us for what is the metal. So remember, we're going to be solving for the specific heat of that metal, and we know that water's specific heat is 4.18. So the last thing that we need to be finding in order to answer this question is the change in temperature of our water and of the metal. And for this, we always need to subtract the final minus initial. So we have the metal starting at 90 and it's ending at 23.4. So that means the temperature is going down by 66 degrees Celsius. I'll leave off those units for right now. And then our water was starting at 22 degrees and going to 23.4. So definitely a much smaller temperature change. 23.4 minus 22 is just 1.4. So at this point, let's start plugging in these numbers. We're going to take our M of water times the C we're looking for. We still need to leave that in there so we can solve for it, times the temperature change of our metal. Sorry, I think I said water earlier, sorry. Now we're on the water side, plugging in M times C times delta T. Even though it's a lot of numbers, we just plug it all in together. And this is when your math teacher would probably use the words to combine like terms. Combine the numbers that are on the same side of the equal sign together. So I'm going to go ahead and multiply together this 55 times 66.6, which gets me 3663. When I multiply those two numbers together, that's also where my C is. So I'm going to leave that there because we still need to solve for that. And then I'm going to multiply all of this other side's numbers together. 250 times 4.18 times 1.4, 1463. And now in order to solve for C, and in order to actually get the C value like we need to divide by the number that's on its side so that this cancels out. And of course, whatever we do on one side, we need to do on the other. So we need to take that 1463 divided by 3663, and we can calculate that the C value here would be 0.39939. And if we look back at our original values, the least number of sig figs that we had was 2. So we should really round this down to 2 sig figs, which would be actually 0.40. Definitely that 9 would round this 9 up. And this is joules per gram degree Celsius, just like you see in all of those table values up top. And that's really going to be the answer to the question. We didn't actually get asked for the value, but we do need to figure out which the metal is. So if we go look at that table, at the top of the page, the C value that is closest to 0.40 is 0.39, which means that the metal is copper. Cu. So make sure you write that in that space because that's the actual answer to that question. Now, let's look at the next question. It's going to be the same format. And our first priority as we read through this question is still find all our numbers. This tells us that a 200 gram sample of metal starting off at 92 degrees Celsius is dropped into a container with 100 grams of water Let's make sure to put a decimal point at the end of that number to make sure we don't have to round down to 1 sig fig. That should have been there already. And the water started off at 26 degrees Celsius. Final temperature of the system is 45.6. What is the metal? So remember, we're still going to be solving for that C value in order to find our metal. And water's C value is 4.18. What we need to calculate real quick with some quick subtraction is our temperature change. So our metal going from 92 to 92 to 45.6 is changing temperature by 46.4 degrees. And our water is going from 26 to 45.6. And that means that it is changing by 19.6 degrees Celsius. So at this point, we should be able to plug in all of our numbers. Take our M of the metal, solving for our C. Oh, delta T is important there. Equals M C delta T. So I want you to try and do the algebra here on this one yourself. I've gotten you set up here, but you should be able to solve for a C value. Remember, that value is going to be joules per gram degree Celsius. I need you to find this number and use that number to tell me what is the metal to actually answer this question. If you need help with some of the algebra, let me know. But I do expect to see you at least try this, and you can check your work because you should end up with a number very close to one of those numbers in the table. If it's not close to something in the table, you need to double check your algebra. But I'm going to leave the rest of this one up to you, because this third question is going to be a little bit different, and I definitely don't want to leave the third one up to you. And what's different here, even as you start to read it, it says that 10 grams of glucose is burned with oxygen in a bomb calorimeter. So this isn't something that's already hot touching something that's already cold. This calorimeter is a special container that helps contain heat and measure temperature changes. And we can do reactions in that container when we can't do them like underwater. I couldn't just do this reaction underwater in order to see how much energy is absorbed by the water, because it's kind of hard to burn stuff underwater. So we have these special containers that help us make these measurements. And the main difference here is because we have a chemical reaction going on, we're not actually going to be doing an MC delta T calculation for one of our sides here. The Q for a reaction, like we talked about on page 11 at the top of the page, is going to be equal to MH. And here, this H technically has a C on it because it's a combustion reaction, but it doesn't really matter as we're solving for that H value there. And so because we're still using this reaction to cause the water to change temperature, then we're going to be taking the MH side. Instead of a metal being MC delta T, our reaction side opposite from the water is going to be MH, and that's still going to be causing the water to change temperature. So we can set that equal to the MC delta T for our water. So with this, we're just going to need to plug in all of our numbers. And here I'm going to show you kind of how I can, if I don't write out those numbers off to the side, we can just make those notations on them here. As we read through, we have that 10 grams of glucose, that's our mass of glucose, is burned with oxygen in a bomb calorimeter with 100 grams of water, so that's our mass of water. The temperature of the water increases by 0.158, so that's already telling us the change in temperature. It's not telling us the final and the initial, it's just telling us how much it changed by. And then because this is more than just water, this is a whole calorimeter, we're not going to be using the C for water. We're going to use the C for this whole calorimeter because there's other substances in here that can maybe absorb some of the heat from this reaction. So still a lot of numbers, but as we read through, we just need to make sure we get all of these numbers in the right places, and then we plug them in. 10 times the H value that we're looking for is equal to the 100 grams of water times that 9.90 value, the specific heat of our calorimeter, times the 0.158 degrees that this would change by. So even though this looks like an entirely different equation, we have created this equation just by setting the reaction energy, Q value, equal to this Q value. It's still Q lost equals Q gained. We're just changing which type of Q we were setting equal to the other one. Technically, we could do an MH equals MH equation as well, if we have one reaction transferring energy to another reaction or causing a phase change. But we're not going to be doing any of those types of problems here. So at this point, I would probably, there's not much to combine over on this side, so I'm going to leave that the same and mostly just multiply all of these numbers together. And at this point, now that I've simplified my expression, just like always, I'd need to divide by whatever number is in the way of me having my answer all on its own. And if I do that to one side, I need to do that to both. And this is going to end up being 15.642. Looking back at my original sig figs, those are all 3 or more. So I'm going to keep this at 15.6. And just like it told me to hope for there, this is kilojoules per gram. We were really calculating the kilojoules over here, the energy from the water, and then we divided by the grams here. So we can see those units coming together into this final answer. Now, you do not need to start working on this page 13 stuff yet. You'll have a little bit of time to work on it in class after you do your lab. But I do want to point out that now that we are done with all of these heat calculations, there is only one calorimetry question on that page 13. Everything else is about one substance gaining or losing energy. There's not two substances in contact, but you can already tell 6 is a little more involved, and it says a sample of metal is dropped into a container of water. As soon as you see that there are two substances there, that means that we're going to be dealing with kind of Q equals Q. Q lost equals Q gained. And I will go ahead and point out that this is a 2 temperature change problem. So this is going to be like those first 2 problems we worked out with MC delta T equals MC delta T. All the rest of these problems up here are either MC delta T problems. If you see temperature changing, that's how you're going to be using, calculating our heat or our energy. Or if there is no temperature changing, then you're going to be using your Q equals MH equation. And I will talk to you more about those and help you with those a bit in class.